Okay, questions, anybody? You ready to finish up chapter 12 and start chapter 15? You see how the pace is picking up? These chapters are shorter. And so this is the point where you're going to start to get behind. If you're not careful, okay? So we're not going to let that happen, right? You did work all during this long weekend, right? No. That's okay. I wanted to clear up something. When we talked about the sharpless epoxidation, I told you that you can make a single enantiomer and you can choose the catalyst. If you use plus diethyl tartrate, you get one enantiomer. If you use minus, you get the other enantiomer. And what I said is that I will not ask you to predict the correct enantiomer for that reaction. Some people interpreted that as you don't have to predict any answers for this chapter. That's just one type. So for example, here's an example here where it says predict the product, and you can get the epoxide where this is wedged. You can also get the epoxide where this is dashed. If you use the minus diethyl tartrate, you get this dashed, and if you use the plus, you get that wedged. You don't need to know that. I'm not going to ask you to draw the single enantiomer that you get. What I want you to be aware of is that this is a way to get a single enantiomer. Question? Yeah, that would you be using the other tartrate, and you won't have to do that. Okay? All right, so then where did we leave off last time? We talked about dihydroxylation, cis and syn and anti. And I left the H2O. This should be H2O, not H2. So you can go back and fix that. All right, and then we want to talk about ozonolysis. And then after that, we're going to talk about oxidation of alcohols. So reaction of an alkene with ozone to yield products of double bond cleavage is called ozonolysis. And there's two different what we call workups. So step one will be ozone. For my class, it's not critical that you include the methanol. It's not critical that you include the minus 60. If you just write O3, I'm happy. And then depending on your second step is the workup. You can get different products depending on what your second step is. If you do an oxidative workup, and an oxidative workup, this is a familiar reagent to you, you would use H2O2. You're going to get a carboxylic acid on one end, and you're going to get a ketone on the other end. So you're breaking your molecule into two pieces, and each piece has a smaller number of carbons than we started with. So we start off with 2 carbons here, and then now each side gets one of the carbons. So we're breaking our molecule into smaller pieces. And right now, there's only one way to do this, and that is ozonolysis. So when you're doing synthesis, if you count carbons, and you have less carbons than you started with, that means you're going to have to do ozonolysis somewhere in that process. So during this reaction, you get an ozonide. There is a mechanism to get this ozonide, which you're not going to need to know, so I'm not going to show you. And the reductive workup, there's 2 ways to do reductive workup. Number 1 is zinc and water, or dimethyl sulfide. So this would be like dimethyl ether, except we have a sulfur instead of the oxygen. You could use either one of those methods for a reductive workup. And as you can see from the products, that the ketone side is still exactly the same here, but on this carbon right here, that's the difference here. This carbon right here, this is oxidized to an OH. Here it stays as a hydrogen. So reductive workup, if we take this apart, basically what we're doing in this reaction is we're cleaving this double bond right here, and each side becomes a carbonyl. So I'm just going to line them exactly up the way they are. Each side gets an oxygen. If both sides have an R, if one side has 2 R groups, you will get a ketone. If one side has a hydrogen, I'm just going to make this X. If one side has a hydrogen, if you use a reductive workup, the hydrogen will stay as hydrogen. If you do an oxidative workup, the hydrogen will be oxidized to an OH. Okay, so that's what you want to keep straight here. Ozonolysis also works with alkynes. With alkynes, we don't have an oxidative workup or a reductive workup. We just use water in our second step. So this is step 1, and this is step 2. So with alkynes, no oxidative or reductive workup. Just water. All right. And so, and that's going to give you a carboxylic acid. Well, actually, a carboxylic acid on the left-hand side. And when there's a hydrogen for an alkyne on the right-hand side, you get carbon dioxide, which, of course, is a gas. And that bubbles away. So we've basically, what we've done is we've taken a terminal alkyne and we've lopped off 1 carbon. So it's 1 carbon less than what we started with. All right, if you have the alkene in part of a ring, then you basically, what you're going to do here is you're going to cleave this. And so this would be, of course, step 1 here, ozone. Step 2 is reductive workup. Again, for my class, it's not critical that you show the solvent. It's not critical that you show the temperature for this particular reaction. So because we have 2 hydrogens here, if we do a reductive workup, then those hydrogens will stay as hydrogens. So here's what we're going to get. Let me fix that. So I'm going to cleave that alkene. I'm going to put a double bond on each side, and the hydrogen's going to stay at hydrogen. Why? Because I'm doing a reductive workup. And that looks like a strange looking bond here, so let's fix that. I'm just trying to make room for this other carbonyl here. So we're cleaving that double bond in half. Each side is getting an oxygen. A little bit complicated mechanism, which is why we're not showing that. You can also write that. This is equivalent to, you can write it like this. So in this case, we're not actually breaking it into smaller pieces, but we are breaking apart the ring and to make a chain from that ring. And really, this is the only way to do that. If instead you do, if step 2 you use H2O2, then your product's going to be the dicarboxylic acid. So this is ozonolysis is a way to synthesize carboxylic acids. We're going to learn about another way to synthesize carboxylic acids in the next section also. Questions on ozonolysis? Anybody? All right, let's talk about oxidation of alcohol. So we're going to use these reagents a lot for the rest of this quarter and also for next quarter. By far the most famous reagent for oxidizing alcohols is chromic acid. It comes in various different forms. I will show you the form that I'm going to use. This one right here. So that's chromium trioxide, H2SO4. You can also do sodium dichromate, H2SO4, potassium dichromate, H2SO4, but the one that I use is the chromium trioxide, H2SO4. I can't say what Sapling or Smith will use. They probably will mix the two up, but they both give the same thing. If you have a primary alcohol, this reagent, chromium trioxide H2SO4, forms a carboxylic acid. So this is a really colorful solution. This is chromium 6. And that's an orange, very deep orange solution. So let's use an orange pen because we got it, right? Orange solution. Very brightly colored orange solution. And you do actually 2 oxidation steps. You first oxidize the alcohol to an aldehyde, and then you keep going. I'm going to put this in brackets because you can't stop here. So can't stop here. We're going to show a reagent that will stop there, but we can't stop here in this reaction. Can't stop here. The reaction doesn't stop here, so this aldehyde is going to be oxidized again to the carboxylic acid. So if you go back to the first part of this chapter where we talked about things being oxidized, this is 2 oxidation steps. So there's our aldehyde. And then we're going to do this more. CrO3, H2SO4. Goes all the way to the carboxylic acid. So this is a second way to make carboxylic acids. So should be another index card showing how to take an alcohol to a carboxylic acid. That'd be a good one to have. I'm going to draw all the side products. I usually do that the first time I introduce a reaction. We have this, H2O. We have SO4, 2-, and we have Cr3+. And so that's how you know the reaction is complete, because you get green, kind of gummy chromium salts. It's actually blue-green, but I don't have blue-green here. I'd have to go into my other colors to do that, but you get the idea, right? Blue-green precipitate. So you start off with the orange solution, you add the alcohol, or you add this to the alcohol. The orange solution color goes away, and you get a blue-green precipitate at the bottom. If you have a secondary alcohol, you get a ketone. So this is the reagent I'm going to use. H2CrO4 is actually unstable. That's what actually forms in the reaction when you mix chromium trioxide plus water plus H2SO4. That gives you H2CrO4. Okay, so, but I don't usually use this. This is the one that I use. So you'll be able to recognize that. And your product is a ketone. Secondary alcohols give ketones. Primary alcohols give carboxylic acids. So as you can see, overall in this reaction, we're replacing, we're getting rid of a carbon-hydrogen bond and replacing it with a carbon-oxygen bond. So we have now 2 carbon-oxygen bonds. I'm going to show you how this works. This is not a mechanism. It's not a complete mechanism, but I'm just showing you how, because sometimes that helps many students to be able to picture what's happening in this reaction, and I want you to be able to do that. Makes it easier to remember it. I will not be asking you this. I remember I said no mechanisms in this chapter. So H2CrO4 has a structure very similar to sulfuric acid, except you have a chromium in the middle instead. And this is a fast and reversible process. That's what happens in the first step. In the second step, we get an unusual reaction that you haven't seen before. It's called an alpha elimination. So I'm going to redraw this chromium species here. So water comes in. So eliminations that we saw in chapter 8 were beta eliminations. This is an alpha elimination. So we're going here. So it looks like that. That's called an alpha elimination. But it looks a lot like a beta elimination. If you think about this hydrogen here, if you think about this as a leaving group, it looks a lot like a beta, right? We're removing this. This breaks, we make a double bond here, and that leaves. It's still, though, it's called an alpha elimination, but you can see if you look at it from the perspective of this leaving, it looks a lot like a beta elimination. All right, so that's what happens. This is the slow rate determining step. And you can see that's how you get the carbon-oxygen double bond. I'll draw all the side products here so you can see where everything's coming from. We're going to get hydronium ion here. And we're going to get CrO, well, it'll look like this. This is chromium 4. And that's reduced further to chromium 3. So it's a little more complicated than this. All right, so why did I go through and show you that when I said there's not going to be any mechanisms? Because I wanted you to realize why tertiary alcohols don't give any reaction. Okay, so no reaction with chromium trioxide. Tertiary alcohols can't be oxidized. And you can see why no reaction. The first step can happen with a tertiary alcohol. So we can form that. So let's draw that for step 1. And I'm sure most of you could draw a mechanism for how this is formed. It's going to be very similar to making a tosylate. So here's what we have if we do a tertiary alcohol. The key step here, the rate determining step, is eliminating an alpha hydrogen. So that's a hydrogen that's bonded to the same carbon that's bonded to the oxygen. Can you see that we don't have one here? We don't have a hydrogen bonded to the carbon that's bonded to the oxygen. And that's why we can't oxidize it, because there's no carbon-hydrogen bond to break. So if we have a primary, there's 2 to break, and we will break both of them. If we have a secondary, there's 1 alpha hydrogen. This one has none. Okay, so that's the key thing here. There's no OH bond to break. So no alpha hydrogen. So there's no alpha hydrogen to eliminate. Therefore, no oxidation can occur. All right, so a lot of new index cards in this chapter. We want to show conversion of an alcohol to a carboxylic acid. We want to show conversion of a secondary alcohol to a ketone. Okay, so those are going to be really important, because if you think about it, we're making carbonyl compounds with these reactions. 51C, there we do 7 weeks of carbonyl chemistry. So we need to be able to make those compounds, and this is one way to make them. All right, there's one more reagent that you need to know from this chapter, and that's PCC. And you can use the abbreviation for PCC. So feel free to use that if you're using it as a reagent. You should know what it looks like, so if I actually draw it out, you'll know what it is. And you do have to write PCC. I get lots of strange answers on tests. I'll get CNN, I'll get ABC, CBS. There is actually a reagent in 51C that's a CBS reagent. And maybe that's the confusion, but it has to say PCC if you're going to use it as a reagent. And this is one of the ones that I would call a famous reagent, which means we use it a lot. So this is a really important one to know. It's a famous reagent that we're going to use a lot the rest of this quarter and next quarter especially. All right, so formation of PCC. It's the same idea. We have chromium trioxide, one equivalent of hydrochloric acid. So this is one equivalent, and this is all combined, and pyridine. Good old pyridine. So we're familiar with all of these reagents here. And so what you get is pyridinium chlorochromate. So here's the pyridinium ion. Once we protonate pyridine, it's pyridinium ion. So it has a positive charge. We've seen that already. And then we get CrO3Cl-. So this forms a salt. These are yellow-orange crystals. And the nice thing about PCC is you can dissolve it in an organic solvent, and it does pretty nicely. It's soluble in, usually you used methylene chloride, soluble in CH2Cl2 is the solvent that's usually used. So if you see the CH2Cl2, that's all that is the solvent. So sometimes that throws students off. We'll just label that as the organic solvent. So this is nice. PCC uses an organic solvent. Chromium trioxide, you can have that in water. You can also have it in acetone. But this is actually a little bit milder reducing agent than chromium trioxide. So if you have a primary alcohol, you can stop at the aldehyde. And that's going to be used endlessly in 51C. Okay, so no over-oxidation is seen. By over-oxidation, I mean the primary alcohol going to a carboxylic acid. No over-oxidation seen. Did I make a mistake? Usually that means no? Okay. No carboxylic acid formed. PCC with secondary alcohols forms the exact same thing as chromium trioxide. The nice thing about PCC is it's milder, and we don't have excess acid in here. We just have one equivalent, one equivalent, one equivalent. If we use chromium trioxide, H2SO4, we have a lot of acid, and we know that that can cause problems with alkenes and alkynes, right? We can get hydration of alkenes and alkynes. So if you have a double bond elsewhere in the molecule that you don't want any hydration to happen, a better way to do this is to use PCC instead. So these guys are all react with acids, as we saw in chapter 10 and 9. These react with acids. Chapter 10 and 11, sorry, not 10 and 9, 10 and 11. Tertiary alcohols, no magic here. It also doesn't work. So tertiary alcohols, no reaction. I want to say a little bit about green chemistry. You won't be doing a chromium oxidation in the lab, and the reason is that chromium reagents have been found to be carcinogenic. Okay, so we used it when I was a student. probably out on the bench. We used benzene. We used all these carcinogenic reagents, so I'm lucky to still be here, right? Anyway, we try not to use it very much. If you use chromium reagents, which you can use, it goes in a separate waste container and it costs a lot of money. So you might not think about the waste that you generate in the lab. The waste people come and take that away and they do whatever they do. The chromium has to go in a separate waste container and it's a lot more expensive. So every bottle of waste that's made in the lab has to be carted away. That's part of what your lab fees go to. You never even think about that, right? So many oxidizing agents in particular are especially toxic, so certainly chromium-6, bad. Chromium-3, also bad. Chromium-3 is your byproduct. So carcinogens, special waste required. So a lot has changed since I was a student here at UCI. When we washed our glassware with acetone, it went right down the sink. When I was a student here, it was fine. We didn't have to put acetone in the waste container, of course, and then it goes right out into the ocean, and I don't think the fish love that very much. But yeah, so things have gotten a lot stricter. Osmium tetroxide's really bad. That's nasty stuff. OSO4. Ozone is also bad. Down here it's bad. Ozone good in the upper atmosphere, bad here. Good in upper atmosphere, bad here. It's also a carcinogen. So people are always looking for alternatives to these very common reagents that are not necessarily very good for you. Special race required, and let's do dollar signs here. Lots of money here. Okay? So one especially nice alternative to conventional chromic acid oxidation is something called amber list. Amber list A226 resin HCrO4-. You don't need to memorize that. I just want to make you be aware of it. We're doing paper chemistry in this class. This is a better alternative. So what the difference with this one, it still has chromium, but it's on a polymer support. So you keep it on the polymer. After you run your reaction, the chromium stays attached to the polymer. And then once it stays attached to the polymer, you wash your reagent off, the polymer stays there, and then you can oxidize the chromium back up again. So it's reusable. And so this is what it looks like. We have this polymer support. It's going to behave like PCC. So it's going to oxidize primary alcohols to aldehydes. And you can actually use it without solvent. So we save solvent when we're doing this reaction. You also avoids the use of the strong acid. It can be filtered off and then regenerated. So here's an example here of using this catalyst, which we really like. It's also really expensive too, which is probably why we don't use it in the lab. But it gives me an idea to try this. We'll have to try that, see how expensive that is. Okay? All right, so just a little green chemistry awareness. All right, I want to move on to designing synthesis part 2. We started this at the end of chapter 11, and now we've learned a bunch of new reagents, so now we can really expand our repertoire and be able to synthesize more complicated things, which makes your life harder. Okay? All right, so we did reactions where we constructed a carbon skeleton. We did functional group interconversion. We did control of regiochemistry. And now we're going to do one that has control of stereochemistry. The first example is not has no stereochemistry, but the second one does. Okay, so here's an example of a synthesis problem. Synthesize 2-bromobutane from compounds of 2 carbons or fewer. Okay, so The ways we've learned to build up carbon skeletons is we take acetylene, we deprotonate, and we add on a carbon, right? We can add on a methyl bromide and ethyl bromide. That's how we're building up carbon skeletons. So first thing first for this problem, let's draw it. 2-bromobutane. 1, 2, 3, 4, 2-bromobutane. We want to synthesize that. There is 4 carbons. So we're going to want to make that from 2 carbon pieces. So I'm going to take this apart retrosynthetically because I know that I can make that compound if I have the alkene and HBr. I can make that from that alkene and HBr. And this alkene I can make from the alkyne. And then if I have the alkyne, then I can build up a carbon skeleton with the alkyne. So we've learned ways to partially reduce an alkyne to make an alkene. So what we would do, we'd probably use H2 and Lindlar's catalyst. If we use H2 and Lindlar's catalyst, then we can get that alkene, and then we do HBr. And so now this one, we've still got 4 carbons. We want to break this into 2 pieces. If we had deprotonated acetylene, and we had, this should be a CH3, by the way. Go fix that. Just caught that mistake. If we had those 2 compounds here, we can build up that carbon skeleton. Each of those have 2 carbons. And then this we can make from acetylene. So do you have the picture in your mind how we're going to do this? We've made a big jump. So for the first midterm, it was 2-step syntheses. Now we're up to more than that. Yes? Did I do it again? Look at that. Okay, thank you. Now, let's write out the synthesis in the forward direction. How this might look on a test. Wow, I don't know what I did there. How this might look on a test. Could be an open-ended synthesis. We'll draw it that way, and then we'll draw it the way it might look on a test. Could be either way. We start off with acetylene. I'm going to deprotonate that, NaH or NaNH2. And then in the second step, I'm going to use, and this time I'm not going to do that same mistake, ethyl bromide. So I call these open-ended synthesis because you write out the products from each step, unless you have something like this where those 2 steps go together. You don't have to show each. So we give a little picture of what's happening here. I don't do too many like this because they're very difficult to grade. All right, what's next? H2, Lindlar's. Lindlar's catalyst. That gives us the alkene. And then our last step is HBr. And there's 2-bromobutane. So that's what I call open-ended synthesis. Or on the test, it might look like this, where I start off with acetylene, and that gives you a little help there, right? You have to know that's how you start. And then you have a box with an arrow in it. And you go to this. And I'm going to warn you, and I'm going to warn you again. Make sure you number steps. So what that would look like is step 1. Let's just pick one of these. We'll do NaH. Step 2, ethyl bromide. Or iodide, or chloride, or tosylate, whatever you like. Step 3, H2, Lindlar's. Step 4, HBr. That's 4 steps. That's quite a leap from what we had in midterm 1. Question? He asked if, did everybody hear that? If you do the HBr step first and then do the Lindlars, if you do the HBr step first, then you wouldn't use Lindlar's catalyst, you'd use palladium. Did everybody follow what he's saying? Let's show that. That's a really good question. Or same step 1, step 2, step 3, HBr, 1 equivalent. We're also to the point where there's more than one way to do it. And so if I write out the key, some TAs will just only give that answer, mark that correct, if I don't anticipate everything that people are going to say. So this is really important from this point forward that you look at your midterm, and if you think you've done something correct that's marked wrong, show it to me and get the points that you deserve. Okay, so if you do this instead, then we're going to have this. HBr here, right? And this will be ethyl. And then in order to get that, now we don't use Lindlar's catalyst, because Lindlar's catalyst stops at an alkene. Then we would use H2 and palladium. Okay, so that's another way to do this. So sometimes you've got a lot of creative people in this room, and sometimes I can't anticipate what you're going to come up with on the test. And so really important, if you do poorly on the test, don't not look at it. That's not going to help you. You want to look at it, see what you missed, and so that you make sure that you don't make the same mistake on the final. All right, this looks a lot harder because it has stereochemistry, but it's not. I'm just going to give you an outline. We're not going to do the whole thing because we're going to do this in discussion. But let's do this. Does everybody see this right here? This is what I hope can jump out at you. We know how to do anti-addition of bromine to an alkene. So I'm going to go retrosynthesis here. This looks overwhelmingly difficult. It's really not. So bromine, and what alkene would I have, the cis or the trans? Trans, the ethyls are on opposite sides. That's what I need. So here's another 2 compounds or fewer, which screams at you use an alkyne. Okay, so we have that. And then I can make that from the alkyne. And then if I have that, and what would I use to go from what would I use to go from here to here? From going from here to get the trans, what would I use? Dissolving metal reduction, sodium, and liquid ammonia, right? And I know you know how to make this from acetylene. Acetylene, we deprotonate. Don't do it all at once. Don't deprotonate both sides and add 2, just add. Deprotonate, ethyl bromide, deprotonate, ethyl bromide. So I know you know how to do that, and so we will finish that in discussion. Questions? Anybody? All right. Here's your chance. We're going to save that work, and it takes a few minutes, so think of something. Maybe ask a question about the midterm next week, something like that. That's coming up. Yeah. Where's somebody? Where are you? Oh, here you are. Yes. Good question. If you use Lindlar's catalyst, you get a cis alkene, and your the 2 ethyls will be on the same side. Okay? All right, chapter 15, we're taking a big leap here. Why? Oh, here we go. Okay. Okay, chapter 15 is different than any other chapter we will do all quarter, all year. It's radical chemistry. And that's important for biologists to study. It's also how we are going to take, we've learned a lot about how to take a compound that has a functional group and change it to another functional group, build up carbonyl skeletons. But what if we have like an alkane with no functional groups? How do we put a functional group on that? This chapter. So this has a couple of key reactions that we were going to need in synthesis. It also has very different arrow pushing. It's radical reactions. And so, but very different than anything that you've seen before. So let's talk about that. A radical is a highly reactive intermediate with an unpaired electron. Radicals are involved in oxidation reactions, combustion reactions, and biological reactions. So electron transport system, when you covered that, radicals involved with that. So here's a radical. This is a carbon radical. So we got a little preliminary to do here before we jump into mechanism. sp2 hybridized. Planar. What does that remind you of? It's a carbocation with one extra. If we threw one electron into the empty p orbital of a carbocation, we would have a radical. Okay, so let's compare that with a carbocation. So this is a carbocation. It is also sp2 and planar. And now we're going to compare that with a carbanion. Very different. Trigonal pyramid, right? So let's throw that negative charge there on that radical. So let's label these guys here. We have, this is a p orbital. It is not empty, it has a single electron. This is an empty p orbital. And this is the lone pair here in a carbanion, this is an sp3 orbital. So completely different structures. And if you look here, carbocation, carbon owns one electron from each of these bonds, right? So owns 3 electrons here. Carbanion here, 1, 2, 3, 4, 5. This carbon has 1, 2, 3, 4. So this would be like if we took carbon straight off the periodic table in its uncombined form, that's what it would be. All right, so some similarities to carbocations, definitely. Stability, free radicals and carbocations both are electron deficient and they follow similar order stability, except, let's label these. This is a benzylic, allylic. Those are both more stable than tertiary, which is more stable than secondary, which is more stable than primary, which is more stable than methyl. Similar, but not exactly the same. What's different? Primary benzylic, primary allylic. What's different? If we know our carbocation stability handout, and you should know that if you didn't learn that for midterm 1, you'll see it again on the final, guaranteed. What's the difference? In a carbocation, what's more stable? Benzylic, allylic, or tertiary? Tertiary is more stable for a carbocation. So here we have, that's flipped. That's the only difference. Everything else is the same. And like carbocations, radicals can be stabilized by resonance. So we have resonance stabilization here. So if you can imagine if this was a positive charge here, That would be an allylic carbocation, and we have resonance stabilization. We also have resonance stabilization here. And so this we would call this something a little bit different. This is a resonance stabilized. Not an allylic carbocation, an allylic radical. So just like with carbocations, you can get products from both resonance structures if they're different. And the same thing happens with radicals. You can get products that you don't expect because of this resonance stabilization. All right, so let's, how are radicals formed? Free radicals are formed when bonds break homolytically. This goes all the way back to, I don't know what chapter it was, one of the earlier chapters. But before we do that, I want to say, and I almost forgot to say, is that we have no rearrangements. No rearrangements with radicals. So they're similar to carbocations, but not exactly the same. We don't get rearrangements. So that makes life easier for you. All right, so we break bonds homolytically. Let's see what that looks like. Hopefully you're feeling a little deja vu because we did this last quarter. We're not used to radical cleavage at all. We're not used to homolytic cleavage. We're used to heterolytic cleavage. So this is what we are used to seeing. The two electrons from a pi bond move onto one atom, usually the more electronegative atom, right? To give charged species. So that's heterolytic. Heterolytic bond cleavage. For radical reactions, we are only moving one electron. We are not moving two. And so these two shared electrons, it's more of a sherry kind of thing. You get one electron and the Y gets the other. So one atom's not getting both electrons. One's getting one, one's getting the other. And when we do that, we get two radicals. That's homolytic bond cleavage. And I want to point out, certainly I want to point out the fishhook arrow. So a double-headed arrow, like we're used to seeing, moves two electrons. Fishhook arrow moves one electron. And compare that with a double-headed arrow moves two electrons. So when you do mechanisms in this chapter, you're going to use single-headed arrows. If you draw your whole mechanisms and it's entirely correct, except you have double-headed arrows, you get no points. You have to use single-headed arrows. Because it isn't entirely correct, because you're not moving two electrons, you're moving one electron. So a little bit of nomenclature, and this isn't really nomenclature, it's more like terminology here. Bromide ion. Okay, this is really difficult here, this part. Okay, that's bromide ion. Bromine atom. Atomic bromine. This is, again, we take it right off the periodic table in its uncombined form. So bromine atom or atomic bromine. Or bromine radical. Or bromine free radical. Those are all interchangeable terms for that. And then there's molecular bromine, which we just call bromine. And that's just bromine in its natural combined state. Okay, so just a little bit different terminology. That's a perfect stopping point. We will continue this next time.